Learn like a pro.
All right, let's jump right in. Look, if the word stoichiometry makes you break out in a cold sweat, thinking about those high school chemistry tests, just take a deep breath. Forget all that. Because today, we're going to flip the script. We're not talking about it as some dry math problem. No, think of it as your very own diagnostic toolkit, like a dashboard you'd see in a high-tech car, for figuring out what's really going on inside a chemical reaction.
You know, in the textbook world, chemistry is just perfect. It's this beautiful, clean recipe where everything combines flawlessly. But let's be real, when have you ever seen reality look like the textbook? The lab is messy. You've got warning lights flashing, right? Alerts popping up for things like contaminated ingredients, bottlenecks in the process, and just plain old inefficient results. And that's exactly where our dashboard becomes so crucial.
So let's just redefine this thing right now. Stoichiometry, it is not just about balancing equations, making sure the A's and B's line up. Nope. It's the set of powerful tools we use to measure that gap, the gap between the perfect dream on paper and the messy reality in the beaker. All right, first things first on our dashboard. Before we even think about mixing anything, we've got to run our first diagnostic. It's all about checking the quality of our starting materials. Think of it as an input alert.
And here's the thing, right? We almost never start with ingredients that are 100% pure. I mean, imagine you're working with something like unrefined coal. What you've really got is a lump of what you want, the pure carbon, but it's mixed in with a whole bunch of other junk. Inactive stuff, filler, maybe just plain old dirt. So the first big question our dashboard has to answer is, how much of the good stuff do we actually have to begin with?
So how do we figure that out? Well, we use this really cool trick I like to call the reverse pipeline. Instead of looking at what we started with, we look at what we ended with. Let's say we made 15 grams of carbon dioxide. Okay, now we work backwards. The math is pretty clear on this. To get that much CO2, you had to have started with precisely 4.09 grams of pure carbon. It's non-negotiable. So even though our scale said we put in 6 grams of coal, it turns out only about 68% of it was actually the stuff we wanted. The rest was just along for the ride.
Okay, so inputs are checked. Now let's move on to the reaction itself. Time for a process alert on our dashboard. We're going on a hunt for the bottleneck. This is a super important concept. In pretty much any chemical reaction with more than one ingredient, one of them's going to run out before the others. We call that the limiting reagent. And honestly, the best way to think about it is baking. Imagine you've got a mountain of flour, but only one single egg. How much cake can you make? Right, only enough for that one egg. The egg is your limiting reagent. It's the boss. It single-handedly decides the absolute maximum amount of cake or product you can possibly create.
So, how do we spot this bottleneck in the lab? Well, it's a two-step process. First, we take the mass of each of our reactants, say magnesium and hydrogen, and we convert them into moles. Now, don't let the word moles scare you. It's just a way chemists count atoms. It's like the universal currency of chemistry. So, our recipe says we need a 1-to-1 ratio. But look, we've got 0.2 moles of magnesium and only 0.1 moles of hydrogen. It's pretty obvious, right? The hydrogen is going to disappear first. That's our bottleneck.
And this is the absolute key takeaway. When we're trying to predict how much stuff we're going to make, we have to base our entire calculation on the limiting reactant. That's it. What about all that extra magnesium? It's just left over. It doesn't matter. For the purposes of our calculation, it's a ghost. All of our predictions, every single one, are tied directly to that bottleneck.
All right, we've checked our inputs, we've analyzed the process, so it's time for the final check on our dashboard, the output alert. The moment of truth. How much did we actually end up with?
And this part is all about comparing the blueprint with what you actually built. On one hand, you have the theoretical yield. That's the perfect on-paper maximum amount of product you could possibly get if the stars aligned. You calculate that from your limiting reagent, of course. Then there's the actual yield. And that's, what you literally managed to scrape out of the beaker after all the little spills, the side reactions you didn't plan for, and just life happening. And trust me, there is always a gap.
So remember how with purity we worked backward from the product? Well, yield is the opposite. We're looking forward. We start with our main ingredient, our limiting reactant, and we calculate that perfect theoretical result. In this example, it's 17.1 grams of copper. Then we go and weigh what we actually collected, and whoops, it's only 9.5 grams. A quick calculation tells us our yield was only about 55.6%. Is that great? Not really, but hey, welcome to real-world chemistry.
Okay, so let's just pause for a second and nail this down, because it's important.
Purity is all about your inputs, and you work backwards from your final product to find it. The question is, how much pure stuff did I start with? On the flip side, yield is all about your outputs, and you work forwards from your ingredients. The question there is, how much of what I should have made that I actually get? See the difference? Inputs versus outputs, backward versus forward.
Okay, before we finish up, I've got a really cool pro tip for you. It's like a secret shortcut on our dashboard. Now, it only works in a very specific situation, but it's a situation that comes up all the time, when every single thing in your reaction is a gas.
This is called Avogadro's shortcut, and it's awesome. Here's why it works. At the same temperature and pressure, all gases are kind of democratic. They all take up the same amount of space per mole. It doesn't matter if it's a big molecule or a tiny one. Because of that, we can completely bypass that whole mass to mole calculation we did earlier. The ratio of moles in the balanced equation, it's the exact same as the ratio of volumes. So if the equation says you need 2 parts of this for 1 part of that, you can literally use 2 liters of this for 1 liter of that. It's just a beautiful, elegant shortcut.
So let's just zoom out for a second and look at the whole master map of our process. We started by diagnosing the purity of our raw materials, our inputs. Then we moved to the reactor and diagnosed the bottleneck by finding the limiting reagent. And finally, we looked at our final harvest and diagnosed our efficiency with percentage yield. Do you see it now? Stoichiometry is not a math test. It's the dashboard. It's the set of gauges that tells you what's really happening when you do chemistry in the real world.
And that really brings us to the final big idea here. This whole concept of comparing the perfect plan to the messy reality, that's not just for chemists, is it? I mean, think about it. It applies to work projects, to your personal budget, even to your fitness goals. So I'll leave you with this question. What's your limiting reagent? What's that one resource or factor that's holding you back from reaching your own theoretical yield? And maybe more importantly, what's the dashboard you're using to check that gap between the plan and the reality in your own life?